Right, our last speaker for this session is Canberk Sanli, who will speak about superconformal indices in n equals 0, 2 quantum mechanics.
Thanks. So thank you very much for the organizers for the opportunity. It's a great pleasure to be here. So as you might notice, it's a relatively specific aim that computing an index, Witten type of an index for superconformal quantum mechanics. So I feel like I need to start with some motivations why we are interested to do so. And despite probably, despite the lack of time probably, let me start by giving a very broad motivations. In general, let's start by reviewing a general motivations for black hole physics in string theory. And of course, the main toolset there is ADS-CFT holography, where we want to compute a superconformal index, and in various examples, starting from the example of Strominger and Waffa, for the first time for asymptotically flat black holes, and more recently for asymptotically ADS black holes, people actually have showed that we can recover the black hole entropy by black hole microstate counting. But in many examples, there is a general question that remains unanswered, and that is like, what is the true nature of, what is the underlying nature of these black hole microstates? And what I mean by that is the following. So in general, there are a variety of supergravity solutions, for example, that corresponds to a specific quantum BPS states. These can be single or multi-centered black holes, black rings, fuzzballs, etc. So to probably just rephrase the question, in other words, we want to know, let's say that we have only gravitational probes in our hands, and we want to know if, with only gravitational probes in our hands, what is the black hole solution, or what is the black hole-like solution that we would observe. And also, furthermore, in the CFT side, in the field theory side, there is a further complication that goes under the name of wall crossing phenomena, which essentially tells us that certain BPS states can combine into to form bound states, and vice versa. Namely, the BPS bound states can also decay into its constituents. So this means that if I want to do a consistent BPS counting, in general, my index should be moduli dependent and should capture this decay of BPS states. So I'm going to discuss how we can possibly address these questions in the lowest dimensional field theory that we can think of, which is CFT1. So there are two motivations from the physical side. One motivation is actually less clear to me than the second one. And that is the framework of giant gravitons. It is known that and the second motivation comes from the multi-centered BPS solutions. And what is common in these two frameworks is that in both of them, one expects to get, at low energies, one expects to get an effective low energy description that is given by 0, 2 supersymmetric quantum mechanics. It is unclear if in the first case you can also get superconformal quantum mechanics, but in the second case, so that will be the main part of this talk, to understand how the conformal symmetry actually appears in the second class of solutions. But of course, this itself might not be so standard. I'm going to start by telling about a little bit what is these multi-centered BPS solutions. Actually, if you already know about Canberk solution, it is also a multi-centered BPS solution. But we are interested in black holes. So long story short, in four-dimensional n equals 2 supergravity, there is two classes of solution. One is the single-centered black holes, and the second one is the multi-centered black holes. And both of them are solutions to the Einstein equations that you will get from n equals 2 supergravity. And the spectrum of these solutions are given by what is known as Benef equation or bubble equation, and it gives you the whole spectrum of multi-centered solution. It essentially it can be thought of as the bound state of single-centered black holes. In a sense, so this is the simplest case, right? So this is the two-centered case, where at the center you have a core BPS charge, and you can have a halo of probe BPS black holes which are orbiting around that core BPS charge. And gamma 1 and gamma 2 are the BPS charges of these black holes. And the Denef equation tells us that the radius cannot be arbitrary, but rather it is fixed in terms of these BPS charges as well as the asymptotic moduli values. So, of course, if we want to understand the quantum nature of these objects, we want to consider a more quantum description in a sense, and that is obtained by considering the D-brane origin of these solutions. So we can ask, like, what is the D-brane dynamics that corresponds to these BPS solution, and so that is given by a specific form of gauge theory in one dimension, which has n equals 4 supersymmetry, and it is so. Unfortunately, I don't have time to explain like how we actually arrive to that n equals 4 supersymmetric quiver theory, but the idea is very simple. Actually, you just study the effective dynamics of the open string modes, which can be stretched between either the same type of stack of D-branes or different type of stack of D-branes. And the first one gives you the n equals 4 vector multiplet, and the second one gives you the n equals 4 chiral multiplet. And you have an effective description for these D-branes, which corresponds to the more like quantum physics of these multi-centered BPS solutions. And interestingly, there are two branches in this quiver mechanics. One is the Higgs branch, and the other one is the Coulomb branch. Higgs branch is only purely described in terms of the hypermultiplets that I have mentioned, and the Coulomb branch is described by the vector multiplets, which describes the position of the D-branes in the non-compact space. And it is the Coulomb branch states that actually correspond to supergravity bound states. So maybe to explain the picture here a little bit, let's say that we are starting from this two-centered solution. Gs is the string coupling constant, and once we lower it, we first arrive to the Coulomb branch description, where we still have the bound state of these D particles, and further lowering it, we have the Higgs branch description, and then finally at very low string coupling constant, these are just coincident stack of D-branes. So just to explain, just to elaborate a little bit on how we actually get it, it's very simple, and the idea actually goes back to 1986. You can do the same thing for supersymmetric quantum electrodynamics, namely you can obtain an effective quantum description in terms of n equals 4 vector multiplet. And here, so the red terms, all you need to do is just to integrate out the hypermultiplet, and then it gives you the effective dynamics of these D-branes in terms of only the vector multiplets, which has 3 bosonic, 4 fermionic, and 1 auxiliary degree of freedom. And then you can ask what is the supersymmetric vacua of this theory, and that is the main observation of Denef, is that you have the same type of bound state structure. So by assigning the supergravity parameters to the D-brane parameters, this is to prove that, like for the two-centered case, it gives you the same spectrum of solutions, and this also generalizes to the n centers, where you have n centers of black holes, and in the quiver branch, in the quiver description, you have n-centered D particles. All right, so this was old result. More recently, these people have showed that actually there exists a very nice limit that you can take in this effective Coulomb quiver description, where this quiver mechanics becomes also conformally invariant. And they have investigated these solutions. They are called scaling solutions. And then we have also showed that this can be actually recasted into a gauged superconformal mechanics, where, because we want to understand the supersymmetric ground states in this gauged formalism, which we won't need today, the supersymmetric ground states actually obtain a geometric interpretation, which is hopefully very useful to do a BPS counting. So in the end, we want to count the supersymmetric ground states in the scaling regime of this quiver theory. This is the main aim, and then hopefully answer some of the questions that I have posed at the beginning of the presentation. in this class of example. All right, so just for completeness, this is the whole scaling query mechanics, and to be concrete, scaling limit just means that we put the fi parameter and also the mass parameter associated to the deBriere mechanics to 0, and then nicely D210 superconformal symmetry appears. So it is just some superconformal algebra for those of you familiar with. All right, so it is actually very simple to prove the conformal invariance. This is the three-center. So these people just studied the three-center case in the first paper, and you can recast. So this is just the bosonic piece of the Lagrangian. You can write it in this form, and of course, in one dimension, conformal symmetry acts as SL2R group, and so you have Hamiltonian, dilatation, and special conformal charge, which is K here, which, by the way, also fixes your conformal killing vector. And you can, by explicit check, you can prove that this theory has D210 superconformal symmetry. So let me, before moving on, because as I mentioned, our main aim is to actually construct n equals 2 superconformal index. But before moving there, let me mention what is actually open problems in this quantum mechanics. So these people in 1999 showed that actually there is a nice Higgs-Coulomb map within this queer theory. Namely, you can map your bound state structure to the states in the Higgs branch. But then, after 10 years later than this paper, these people showed that actually there is a sector of states which they called the pure Higgs states that do not have a Coulomb equivalence. And what is interesting about this sector is that they make the dominant contribution to the index. So in a sense, they are the dominant sector if you want to compute the black hole entropy, for example, that corresponds to this system. But we know that it is the Coulomb branch that corresponds to supergravity description. So it is a curious question, what is the fate of these pure Higgs states? Do they survive into the Coulomb branch? Or do they don't appear, and do they look like scaling solutions, or do they look like just single-centered solutions? These questions are also relevant for the series of papers established by Manshot, Piolin, and Sen some years ago, where they had computed the BPS index. And this question that I have posed lies at the heart of some complications also in their work. And there's also some related motivation through ADS2 CFT1 construction. Okay, so in the remaining time, I will very quickly mention what is actually the superconformal index we can write for this class of theories. Just to be clear, so this class of superconformal mechanics is actually known to be very relevant for holography. But up until now, there was no formulation of a superconformal index for various technical problems, and I think we managed to overcome those. So this is the generic n equals 0,2 superconformal mechanics, just sigma model, first studied by Michelson and Strominger and Papadopoulos. So they have obtained what is the geometry of the target space that corresponds to these nonlinear sigma models. And the geometry is what is known as scalar with torsion geometry. But again, for the index, we won't need the details of the geometry. So what we need is more like the superconformal algebra of this superconformal mechanics. And it is SU1,1/1 superconformal algebra. This is, so let me just introduce the components. From the bosonic piece, we have dilatations, Hamiltonians, special conformal charge. We have supercharges, and the commutator with the special conformal charge gives us the conformal supersymmetries. However, this form is actually not useful at all to construct a Witten index. Why? That's easy, because H here wouldn't have any, it has a continuous spectrum which violates the main assumption of writing a Witten index. And the resolution to that is actually very well known from the very oldest papers on conformal mechanics. you need to go to a different basis and express your supercharges and other generators in this basis, where, for example, in the new basis, the supercharges appear as the combination of your supercharges and conformal supercharges, and your bosonic generators become more like Virasoro like generators in one dimension. Okay, once we are in this basis, very nicely we obtain a discrete spectrum consisting of chiral and antichiral multiplets, and we also have a long multiplet, which is just the combination of those two. So, at least before finishing the talk, let me give you the index. So this is the index. What is the content of this? As you might have noticed, so this equation here gives us the BPS bound of the superconformal algebra, and so it is why so that quantity appears here as kind of an auxiliary Hamiltonian, and a crucial tool in our work is establishing what is a proper refinement for this class of superconformal algebras. And perhaps interestingly, it is not the exact R-symmetry of the superconformal algebra, but it differs from that through an action on the fermions. Whether this has some deep physical meaning or not, like if we want to interpret this in terms of higher dimensional superconformal field theories, that's an interesting question. So in the end, this is a well-defined count of the spectrum of a theory that realizes SU1, 1 / 1 algebra. And then how do we do that? We just write the index as Euclidean path integral and apply the standard tricks of supersymmetric localization, and then we can obtain the most general result. Let me very quickly go over like the simplest example. The simplest example is the free particle, and in that case, so this is just a refined Witten index, right? With auxiliary Hamiltonian, and the auxiliary Hamiltonian differs with the original one through this auxiliary magnetic field. So in a sense, the superconformal index, n equals 2b superconformal index for the free particle is equal to refined Witten index for the Landau problem. That's the core of the result. I am skipping that. Of course, we know the whole spectrum in this case. We can compute it. It is this, and then we can compare it with the path integral result. It nicely matches, and then finally generalize it to the most general case, where we obtain a nice fixed point formula. So I guess I'm out of time. I'm happy to answer discuss more if you have further questions. So these are some open questions, I think, related to this issue. Thank you.
We have time for some questions. So if you were to then compute an interacting theory using localization in this setup, would you be using one of the superconformal supercharges to localize?
Yes. So the localizing supercharges are these. Yeah, I had to be very quick in that. It is precisely these calligraphic G's. So let's see. So these G plus and minuses, they are just the combination of the original supercharges and the conformal supercharges. And in the supersymmetry localization, you first need to find what is the BPS saddles that corresponds to the supercharges.
But does the or the square of your localizing supercharge contain any of the conformal generators in this case?
Square of the supercharges is more like the auxiliary Hamiltonian, I would say. Right? So let's see. So this is the algebra. So are you asking this relation? So what do you mean by the square? You mean the anticommutator maybe, or?
Yeah, well, for a single supercharge, it's the square. But so
yeah. So in this case, so the anticommutator with the Hermitian conjugate gives you the auxiliary Hamiltonian, which you use in your index.
Okay, so no, there's no dilatation or something like that in the square of the...
You mean here? No, because sorry, it of course appears there because I mean special conformal charge appears there. It's not dilatation, but as zero is so that actually lies at the heart of the complication, right? Because H doesn't have a discrete spectrum, but K creates a harmonic oscillator like potential, and then it gives you a discrete spectrum. And it appears on the right-hand side of the BPS map. I'm not sure if that answered your question.
We can talk later.
All right.
All right. Yeah.
So in the start of your talk, you mentioned the wall crossing formula,
Yes.
right? Wall crossing formulas can also be written for n equals 4. So can we do all of this for n equals 4 as well?
By wall crossing formula, you mean Kontsevich?
Yeah. Well, I think that one was for n equals 2. I think the n equals 4 was done before n equals 2, if I'm not wrong.
You mean n equals 4 supergravity or what? So n equals 4 theory here is just the quiver theory. It's the one-dimensional theory.
Okay, I see. So you think that doing it for n equals 4 is easier?
So I think there should be a reinterpretation of the wall crossing formula also in the one-dimensional theory. Because it is the same BPS bound states, and
Okay.
I guess that should be captured by through the that I didn't include, but similar to that we have studied the representations of SU1, 1/1. We can also study the representation of D2 0 superconformal algebra, and then there we see that actually certain long multiplets can be written in terms of certain short multiplets, and
Yes.
My intuition is that should be related to the wall crossing in the one-dimensional theory. But
okay, I
yeah,
see.
that's actually one of the issues that we want to address.
Okay.
Because I didn't mention at all, like I started with that quiver theory, which has n equals 4 supersymmetry, but of course we still need to generalize our n equals 2 index to n equals 4. And there the relevant beast is D210 superconformal.
Okay, thank you.
Any more questions? If not, thank you again.